Hello, and welcome to this video tutorial focusing on the I/O pin planning features within the Vivado Design Suite. The Vivado Interactive Design Environment allows you to visualize the various I/O and clock logic device resources to help you optimize the connectivity from the printed circuit board on and off the FPGA. A lot of various factors contribute to a proper I/O pin definition, such as the proximity to other components on the printed circuit board, high-speed interfaces that have to interface with the FPGA, as well as the internal resources on the FPGA, such as the PCIe and high-speed memory interfaces, and other various clocking resources. Designers can examine the various trade-offs and make intelligent I/O planning decisions. You can also do your I/O planning at any stage of the design cycle. Prior to having any RTL sources, you can bring up an empty project and either create ports or import ports and do your I/O planning. You can also do your I/O planning after RTL or even with just an RTL header. The most effective means to do I/O planning is after synthesis. Then you've got a netlist that's clock aware, and a lot more DRCs are available to allow you to interactively place the I/O ports DRC correct, as well as validate the final I/O pinout. Some of the other features allow you to define the device configuration mode and to validate your multi-use pins to make sure you don't have any conflicts. You can also define alternate devices. Sometimes designers are unsure what the actual final device will be for their design, and you can ensure that the pinout selected will work across multiple devices. There are several placement capabilities to allow you to interactively place ports into the package view or into the device view in order to optimize your system-level connectivity. This placement is all done DRC correct to ensure you end up with a legal and desirable placement. And finally, you can export the I/O pin configuration to the printed circuit board designers so that they can build schematic symbols and enter the printed circuit board design. You can also export IBIS models for signal noise analysis. Both the DRC and the printed circuit board interfacing are covered in separate videos and are not covered here. I'll first show you how you can do device exploration and I/O pin planning prior to having any RTL sources. To do that, I've invoked the Vivado Integrated Design Environment, and from the Getting Started page, I'll use the Create New Project link to create an I/O pin planning project. An I/O pin planning project is basically an empty project which you can create or import ports to do initial I/O planning. Notice that after I select the I/O pin planning project type, I'm presented with a menu to either select a CSV or comma separated value file, which is a spreadsheet. Oftentimes designers use a spreadsheet to initially capture their list of IOs. Or I can import an XTC constraint file, which I may have already had prepared. Or in this case, I'll elect not to import any IO ports at this time and open an empty project. And then I can define a target part. In this case, I use a small part, the 70T Kintex device with a 676 pin package. Notice the Vivado IDE looks a little different than your traditional project-based flow. I don't have any sources in the sources view or in the netlist view, and the environment automatically comes up with the I/O planning view layout displayed. Notice also the flow navigator is abbreviated to only show me commands that deal with I/O planning. I can visually examine the device resources in either the physical package view or the internal die within the device view. Notice I can also use the tile vertical command to display both of these views simultaneously. This is helpful when I want to examine the relationships between the external pins and the internal die pads. I'm also presented with the package pins view, which is a table list of all of the package pins sorted by I/O bank. I can expand these at will, and notice a lot of the information about the various pins is displayed in the table. As I/O ports are assigned, the table will be populated with more information. All of these views cross-select. So in other words, if I select an I/O bank in the package pins view, it's displayed for me in both the package and device views. Notice here you can see the relationship of where that I/O bank exists on the physical package as well as the internal die. The properties view will select information about any selected object, whether it be an I/O bank, I/O port, clock region, etc. The clock regions view displays all the clock regions that exist in the device and allow me to select them from this table to visualize them on the device. The capability to visualize both the external and internal domains is critical for doing I/O pin placement. For example, you may have a high-speed interface that has to interface with the FPGA on one particular edge of the device. Notice here I can select the pins that I may want that interface to connect to, and then I can look at the device view to see what ramifications that may have on my internal design. Notice here I can examine that connectivity and make trade-offs to determine the best place for that high-speed interface to connect to the FPGA. I can also look at the internal FPGA device resources, such as the PCIe in this case, to define where I might want to locate logic or the IOs related to that logic that interface with the PCIe. It might make sense to select a clock region that's adjacent to the PCIe to limit the connectivity lengths. I can examine and plan other interfaces onto the FPGA, such as the gigabit transceiver devices and their serial I/O. If I'm unsure where those logical resources exist on the device, I can use the find command. Notice the find command has the capability to search for sites, tiles, I/O banks, and clock regions. In this case, I'll search for all the sites that are of type GTX channel, which will highlight all my gigabit transceiver sites. I can do the same thing for types such as buff-Gs. In this case, you can see where all the buff-Gs are. They're relatively small sites, in case I wanted to hand place any of my buff-Gs or any other related clock logic. I'll now zoom into the clock logic resources associated with one of the I/O banks. Notice the clock-capable pins are shown with a different color along the I/O bank. These clock-capable pins are also displayed as a hexagon within the package pins view, as opposed to the round shape for the regular I/O pins. This visual differentiation helps me quickly identify the clock-capable pins. In the package view, I've also got the capability to turn on differential pin pairs. Notice that when I turn them on, I can visually see the P and N pins associated with all the diff pairs on the device. Another handy feature of the package view allows me to toggle whether I'm looking at the package from either the top, which is the default, or the bottom of the package. Different printed circuit board designers tend to visualize these parts from different orientations, and this feature allows you to toggle which orientation you'd like to view. Notice also on the device view there are a variety of clock logic device resources around these clock-capable pins. There's buff-Rs, I/O delay controllers, input and output FIFOs, O-logic, I-logic, and all the different clocking logic associated with each clock region. Designers can hand place clock logic onto these sites for ultimate control over placement of those objects. Some of the other things to consider while doing I/O planning, the 7 series devices do have different range I/O banks. There are high range and high performance banks, and you need to differentiate between those when placing your I/Os. You also need to consider how you're going to be configuring this device from the printed circuit board. Various configuration modes require dedicated I/O pins in order to be used. I can use the Set Configuration Mode command to select the configuration mode I want to use on this design. And notice when I do so and apply it, it will automatically assign prohibits to those I/O pins. Notice here I've selected a simple JTAG configuration, which only requires one pin. However, some of these configuration modes are quite complex. Notice that when I select this one, it basically uses an entire I/O bank just for configuration. This has to be determined up front to ensure that I don't inadvertently use those I/O pins when I'm assigning my I/O ports. After you've selected the configuration mode, you can open up the package pins view and sort the list by config pins. Notice here there are quite a few of them, and the multi-use pins you need to keep an eye on to make sure you don't need those for other features in your design, such as PCI, memory controllers, and so forth. The package pins view can be flattened and sorted in a variety of ways and displays very useful information about the package and the design. Another handy I/O pin planning feature is the ability to set alternate devices. At the time I'm doing my I/O pin assignment, I may not be entirely sure of the exact device that my design will ultimately end up being in. It could get bigger, it could get smaller. So I'd want to define a pinout that works across a variety of different device sizes so that I can have some flexibility there. Notice here I've opened up another project which targets a much larger device, a 325T. Here I'll use the set part compatibility command, and notice it gives me a list of all of the other devices that are available in this 676 package. I'm using the 325T, so I'm going to set the 160 and the 70T devices as compatible devices. Notice that when I do that, it automatically prohibits 2 full I/O banks here on the bottom of the device. In other words, when I'm using one of these smaller devices, these I/O banks are not bonded out. Therefore, I shouldn't be assigning I/O ports to them if I want to maintain compatibility. I'll now switch back to my 70T project and walk you through some of the specific commands associated with I/O pin planning projects. I have the ability to create I/O ports on the fly using the create I/O ports command. I can create a single port, or in this case, I'll enter a my bus. I can determine the direction of the bus, whether it's a differential pair bus, the width of the bus, the I/O standard, drive strength, slew type, pull type, and interim type of that particular bus. Notice when I do that, it creates a set of I/O ports in the I/O ports view. I can select these individually or as a bus and use the various placement commands to place those either into the package pins view or the device view. We'll cover the interactive placement routines a little later in this demonstration. Another way to populate the I/O ports view is to import the I/O ports. Notice I can import I/O ports from a variety of different import sources, those being a CSV spreadsheet or an XTC constraint file. Here I'll select the spreadsheet, and notice the I/O ports view is now populated with those ports that are in the spreadsheet, categorized by bus. The required format for that spreadsheet is defined in the I/O planning user guide. Or you can use the export I/O ports command to create a template. The other commands, report DRC and report noise, are covered in a separate video demonstration and not covered here. The I/O port configuration can be exported for use by printed circuit board designers or others in a variety of different formats. This is also covered in a separate video tutorial. And finally, after you've done your I/O port assignments and you wish to migrate this project into an RTL-based project so that you can proceed down through the design flow with it, you can use the migrate to RTL command to do that. Notice it converts the I/O planning project into an RTL project, and the sources view now has a io.v file, which shows all of the I/O ports declarations, as well as the XTC file containing all the I/O constraints. Now let's switch gears a little bit and show you how you can do I/O pin planning after you've got RTL and after synthesis. So I've now opened up an RTL-based project that has all the RTL files associated with the design. It could also just contain an RTL header file, which would allow me to proceed with RTL pin planning. Within the environment, I can do pin planning at several different stages. Prior to synthesis, I can open up the elaborated design and do RTL pin planning prior to synthesis. Or after synthesis, I can open up the synthesized design, and now the design is more clock aware, and I can do more intelligent I/O pin planning based on the netlist. I could also simply run implementation and let it assign the I/Os. Now bear in mind though that for 7 series devices, since there are different voltage I/O banks, Xilinx enforces that all of the I/Os get manual assignments for both the package pin and the I/O standard constraints to assure that those constraints have been assigned with forethought. There is a DRC built into the generate bitstream command, which will fail if this condition is not met. So given that requirement, it is imperative that the I/Os all get manually assigned prior to running implementation. Let's look at the constraint file to show you what those constraints look like. Notice the I/O standard constraints are defined for each port in the design, as well as the package pin constraints. Having these constraints successfully assigned to each I/O port will enable you to successfully run through implementation and generate a bit file. For the sake of this exercise, I'm going to select an XTC constraint file that only has timing constraints assigned to allow us to then interactively place the I/Os and I/O constraints that are required. Let's first examine how we can do I/O planning prior to running synthesis by opening the elaborated design. Once the design is opened, I can select the I/O planning view layout to present views more applicable to doing I/O planning. Notice I can see the package view, the package pins view, and I can split the screen again to show both the package and device view simultaneously. Notice the RTL netlist view provides me a hierarchical view of the RTL netlist. I do not have direct exposure to all of the clock logic and various design resources that may be available in my design. Since the elaborated netlist may not match the actual synthesized netlist, it's risky to do anything but I/O planning at this stage in the design. Notice in the package pins view, I see the red default word. As I mentioned earlier, Xilinx enforces that you manually assign both the I/O standard constraints as well as the package pin constraints. This red text is indicating that you have to do that prior to moving forward with your design. There are several commands available under the elaborated design menu in the Flow Navigator, including report DRC and report noise, which are covered in another video tutorial. I/O ports can easily be sorted and selected and placed either into the package pin view or the device view. These commands are identical either in the elaborated design view or in the synthesized design view. But in the synthesized design view, the design is now clock aware, which enables a much more robust set of design rule checks and capabilities. Since they're the same, let's go ahead and open up the synthesized design and walk through I/O pin placement. In the synthesized design, I've got the actual synthesized netlist, which includes all of the clock components and clock logic, which I could elect to assign constraints to, which would be adhered to through implementation. Notice again the I/O ports view displays all of the ports that I've got defined in my design in a categorized fashion by bus. Notice I can see the differential pair signals that are associated with the GTs in the design, as well as all the other signals. This particular design has two large USB memory interfaces, and the port names associated with those interfaces are differentiated with an _0 or an _1. I can group these ports together into interfaces to allow me to better place and manage them. Notice here I use the search command to search for all of the ports that have an _0 associated with them and create an I/O port interface called USB 0 by using the create port interface command. I'll do the same thing for the USB 1 signals. And now notice in the I/O ports view that all of those associated ports are now grouped into subfolders for USB 0 and USB 1. If I expand them, you can see all the various buses and scalar ports associated with that interface. This allows me to select and place all of those ports simultaneously. I can then start assigning these I/O ports by selecting the I/O port interface and using any of the three I/O port placement modes. Notice the three modes including place I/O ports into an I/O bank, place I/O ports in an area, or place I/O ports sequentially. Let's use the first one, I/O bank. Notice that when I select it, I can then drag the ports over either the package view or the device view, and it will place them into the various I/O banks that my cursor is over. And notice here I've placed the entire USB interface into one particular I/O bank. I'll use the upper half of the chip for that USB interface and the lower half of the chip for the other. To demonstrate another method for placing ports, I'll zoom into the device view around that I/O bank. When I select the USB 1 interface, I'll then use the place I/O ports into an area. It allows me to define a rectangle either in the device view or the package view to place those I/O ports in. And notice the tooltip tells me how many of the ports are being placed in the rectangle size that I've drawn. And here you can see that the port placement was done within that area. And to demonstrate the last I/O port placement mode, I'll select the GT bus, which contains the differential pairs for the GT. Now notice by using the place I/O ports sequentially, I can go down the right side of the device here and place the GTs in order that they appear in the I/O ports list. Here, as you can see, I can have direct control over the order in which I place them either in the device view or in the package view. And I'll place all of the GTs from top to bottom here on the right-hand side of the device. I'll then also select the reference clocks that are associated with the GTs and use the same method to place those in order down the device. So as you can see, the interactive I/O port placement routines allow me ultimate flexibility in how I want to place my I/O ports, either based on the printed circuit board connectivity or the internal die connectivity. Being able to visualize both domains helps me tremendously to make the right choices. The icons next to the ports in the I/O ports view keep track of the state of the port. Notice the yellow boxes with checks in them indicate that that port has been placed, and the unplaced ports display with a gray icon. And you'll notice that I still have a few I/O ports remaining that are unplaced. I could use the same routines to place those, but in this example I'll show you how you can use the automatically place I/O ports command to finish the job. Notice the dialog allows me to keep the assignments I've already made or start from scratch. Here I'll elect to keep them, and it tells me it's only got 9 additional I/O ports to place. And you can see it's placed those DRC correct. So this will give me package pin constraints for all of the I/O ports in my design. As you recall, we still need to assign the I/O standards to those ports. I'll expand the I/O ports view and flatten it and sort by I/O standard. I'll then select all of the I/O standard defaults, and I can use the configure I/O ports command to select the proper I/O standards for them. In this case, I'll go ahead and select the default. And notice when I do that, the red word default no longer appears in the I/O ports view, and these have been manually assigned and are ready for implementation. To be sure, I can run the DRC checks to make sure that my design is properly constrained prior to implementation. And here you can see that it is. So I've now made all of these constraint assignments in memory in the Vivado Interactive Design environment, and now I need to save those to my constraint file. If I use the Save Constraints command, it will write them into the end of my existing constraint file for use in implementation. If I wish to preserve my original constraints file and create a new one with my new assignments, I can use the Save Constraints As command and create a new constraint set. I'll elect to make it active, which will make it the default constraint set used for implementation. And as you can see, that constraint file now contains all the package pin and I/O standard constraints required for implementation, and to satisfy the DRC checks in the generate bitstream command. And if I really wanted to take it to the next level, I could use the I/O placement to define my floor planning strategy in the device. As a simple example here, you can see I've taken the USB interfaces and floor planned those, and then some of the other critical modules in the design. Notice you can really clearly plan the data flow through the device using this method. And finally, since we are in the synthesized design, I have a much more extensive list of DRC checks that I could run to validate the design prior to implementation. As mentioned earlier, the DRC and report noise commands are covered in other video tutorials, as well as the ability to interface with printed circuit board designers using the export IBIS and export IO commands, which are also covered in another video demonstration. So in summary, the Vivado Integrated Design Environment allows you to visually examine the device and design resources in a variety of different ways to optimize the I/O and clock placement. You can look at the overall system-level connectivity by visualizing both the external I/O pin connectivity as well as the internal I/O die pad relationships. You can examine the I/O proximity to the relationships of the internal resources such as the PCIe, gigabit transceivers, and other internal device resources. I/O planning can be performed at various design stages, including prior to having RTL, after RTL, and after synthesis. The farther down the flow, the more automated design rule checks and interactive design capabilities are made available. There are also a variety of interactive placement and validation capabilities built into the environment. There are other I/O planning related video tutorials available. You can also refer to the Vivado I/O pin planning and clocking user guide, as well as the specific device documentation such as the printed circuit board design guide, I/O and clocking user guide, as well as the serial I/O user guide. There's also an I/O and clock planning tutorial to help to get you up to speed quickly. Thank you very much for your time.